So the one good news, sir, before the audience are already there. We are not live, right?
No, no, we are not live. And I hope YouTube live is not there, sir. Tanmay, sir?
I am just activating that YouTube link because it takes some time. So I need to do that.
Sir, it's live now.
Okay, okay, that's fine. Maybe we'll chat later on that.
Yeah.
Okay, good. So maybe I think if professor is there, let's start with professor. It's right, Sumit. Better.
Okay, perfect.
And then I can go and then Luca can join.
Okay. Perfect. We will start exactly at 4. Okay.
7 minutes more, yeah.
Yeah, 7 minutes to go.
I have just shared that YouTube link actually for today's event. You can hear me. Share it on your WhatsApp. YouTube link for today's webinar.
Ciao, Luca. I hope you can hear me.
Yes, hi Ratnakar. Good afternoon.
Good afternoon. Good. So I think we have professor also joined. You're also there. So we will start in another 4 minutes.
Okay, yeah, no problem.
Okay. Thank you.
Okay.
So we are live now. And first of all, greetings of the day to everyone. We welcome you all to our webinar series. So this is the third session of this series, third webinar. My name is Sumit Pathak and I'm working as Deputy Manager at McAfee and will be your moderator for today's session. This technical series is organized by Institution of Engineers India in association with McAfee Environmental Solutions Private Limited and proudly supported by Federation Internationale de Biotech, which is also known as FIB. The topic for today's technical session is intercepting rockfall using advanced flexible solutions. In today's session, we'll be having 3 presentations followed by question answer session in the end. A brief about FIB. This series, supported by FIB, reflects its ongoing commitment to excellence in engineering. FIB is a not-for-profit association with members in 104 countries, is dedicated to advancing concrete construction technical, economic, aesthetics, and environmental performance. Their contribution through their FIB bulletins, events, workshops, and courses are invaluable. About McAfee, headquartered in Italy, we are 140-year young organization with sales spread across 130 countries with more than 3,000 employees, 23 factories, and 70 subsidiaries. McAfee Indian subsidiary was incorporated in 1998 as McAfee Environmental Solutions Private Limited. Since then, we have been associated with some of the most prestigious construction projects across the country. Now, to begin with this session, I would like to call Dr. Dr. Juneja to start our first presentation. Dr. Juneja is a professor at IIT Bombay and has been at this institute for over 18 years. He has earned his doctorate from NUS Singapore. He holds master's degree from IIT Delhi and bachelor's degree from University of Roorkee, which is now known as IIT Roorkee. Dr. Juneja worked in the industry for over 6 years in India and UK before returning to academia in 2005. Now I would like to call upon Dr. Juneja.
Yeah, thank you, Mr. Sumit, for the introduction. Just I think you would be able to see my first page.
Yes, sir, it is there.
Yes. I'm really grateful to McAfee for inviting me for this presentation, which is hosted by the Institution of Engineers and FIB. So the topic is in fact quite an excellent topic. It's about how the rockfall events have led to us better understanding of developing better improved solutions. So I have listed down one case study which in fact I would say it's more of a pioneer case study for the railways, especially along the western coast, wherein they have, based on the success of this case study, they have in fact developed a multiple, what do you call it, copies of or improved copies of the, the mitigation process, which was first used in way back, I think about just before a year or two before the COVID event. I will start with the case study, which is famously known as Monkey Hill Station. Monkey Hill is about 100 kilometers away from Mumbai. It's in fact, if you're on the way to Lonavala, you will probably see if you're, the train invariably halts at this station, and it's a good scenic view. While people think it's more like a scenic halt where people get down to take photographs in unknown position, but the halt is because the trains have to, have an extra engine to push the train further up the hill. So it's just an add-on where the engineers, add on extra push or extra energy to pull the to make the train go further up the hills. So this is at this location, there have been numerous past failures. Way back, where the data, all the data has been shows that along a stretch, failures have happened where rockfall events, debris flow, landslides have been occurring, almost every monsoon. So I will pick up these small histories which we have tabulated. I will also briefly cover what was the geotechnical and hydrological studies, at least if not the what do you call it, the entire process, but what really was the outcome of this study. I'll speak on the finally what is the strength and stability of the whatever is the process we followed and the solution which was used. And in fact, the best part is the solution was time tested a year after the installation, and this entire package was really, I would say, an eye opener for us. And thanks to McAfee, because they were the partners involved in the what do you call it, in the execution of the project. So give you a brief background on this entire Lonavala. So it starts from Karjat. Karjat is where, not a station not far from Mumbai. And where in Karjat Lonavala section, this hilly terrain has his, let me see if I can get a pointer. Yeah, I think this is better. It has several tunnels. And these tunnels are, if you look at the numbers, in the entire 28 kilometers, you have 27 tunnels. So it's really a very, what do you call it, a geotechnical challenge, this entire terrain of Sahyadri range. The heights of these hills go right up to 600 meters. One side of the section of the slope has steep cliffs and gorges on the other side. So it's really a very, again, as I said, geotechnical challenge to have entire railway line run through this terrain. This region receives 3,000 millimeters plus of rainfall each year. This is a large quantity compared to the short duration of monsoon months we have in this, in the entire year. Just 3 months of monsoon and you have 3,000 millimeters of rainfall. It's a big chunk wherein you see, because of which you have streams, rivers, and a large quantity of eroded material and deposits which pass through it. So huge amount of erosion occurs during this. And these erosions, they kind of carry the, whatever is the jointed material between the rock cliffs, it just removes them, helps degrades them. And it's because of these joints, they are widely spaced and they have loose pockets of rock. Therefore, there is a perennial, what do you call it, threat to rock stability when the cliffs get exposed to the wide variation in the temperature, humidity, and rainfall. So there is, what do you call it, an extensive database maintained by the Central Railways right from 2006 to 2017. And as a first instance, all these rockfall events have been, what do you call it, labeled or tabulated along this stretch. So it's just about a kilometer plus long stretch. And we kind of made it as a more like a pilot study. So what you see over here, that's the hill. We call it Monkey Hill. It's a Google map, so probably not so clear at this scale, but the station is somewhere there where you see the pointer. So you have these tracks coming from Karjat, Mumbai, and somewhere here, the what do you call it, downline goes along this stretch, comes over here, and the upline back here comes along the other side and goes there. So that's the thing. If you look at, I'll run a short few second animation. It'll show you dots along this stretch, colored dots. The size of the dots, of course, mimic the size of the landslide or the rockfall event. Incidentally, landslide has a slightly different symbol, but let me see if you can catch these symbols as I run this video for next 10 or 15 seconds. It has an array music. I just put it because to show that how, what do you call it, dangerous this entire situation is. So it starts from 2007, 6, and right goes each year. These events are larger each year. I think that's it, too short. But nonetheless, what you see is the number of rockfall events have increased. That's for sure, because people always worry about how the extreme weather conditions cause this. So it's just like, a few days in a year, which is good enough to cause, substantial damage. And it's also noticed that big, new and bigger hazardous locations have emerged in these past few monsoons. And as an eye opener, in 2017, it was in big news that boulders, they crashed through the engine of the Mumbai Hyderabad Express, and it pushed the train off the track. So I think 3 buggies were off the track. The same year in August, a boulder punched through the Hubli LTT Express. Fortunately, in both these incidents, there was no casualty. But just a year later, if you see this, a year later, again, the boulders fell down on the tracks. If you look at the right-hand side photographs, these photographs are incidentally, I would say, not shown in the newspaper. So what you're seeing is something which probably is top secret for now. Look at the size of the boulders. It's huge. So these incidents, in fact, made the railways to take serious note of the above incidents, and they needed some, a more permanent solution, and which rather than the routine solution, I would say routine examination they were having, wherein a person walks down the track every morning, sees if there's been any incident over the night and reports to the nearest station. So that is more like, needed something better than a person each day reporting what is happening. So that was the main objective or the main cause of, the start of this entire exercise. I've said this, told you about Monkey Hill Station. It's a really a vulnerable spot because it lies at an elevation of over 400 meters, sorry. And like I said, it's a technical halt wherein all trains do stop at this station. This study was selected again to evaluate the safety and stability of the hill. So I said, that's the line which goes, right from Kajra towards Lonavala. And the white color is something which comes back. Okay. If you look at the geotechnical properties of this, stretch, it's a wide variation, and it's in fact, what do you call it? A very complex and wide, should say. It has thick residual soils mixed with pyroclastic material. So volcanic ash, that's the weakest material I find in a mixture of cobbles, ash, everything, right from, what do you call it, unbonded material, you would say, as a fill material between the behind the rocks or in between the rocks. There are also you can also see some friable laterites. They appear as individual spots. And at several locations, you can find weathered and disintegrated basalt rock, which is mostly exposed. And it's the exposure over the decades which has caused this rock to disintegrate and weak. If you look at the geotechnical properties, in fact, you won't be surprised to see that the properties do not indicate that, what do you call it, you have such a material can, cause failure, weakness in the soil, because you look at the strength property, you look at other E values, they're pretty high. So geotechnical properties, I would say, it would be meaningless in such an area, primarily because it's the fill material which is actually fails, and it's because of the fill material in between the boulders and rock, the disintegrated pieces of rock as well, which causes failure. And you're not really going to do too much other than appreciate what is the some very basic properties you can obtain from the geotech report. So mainly, I would say it's the first thing is what you do is from the survey. And I think the best thing we got done was probably maybe for the first time itself was a drone survey which was done for this area. Now, drone at that time was something wherein, not very common, I would say. You will not really find a very, what do you call it? How do you put it? People who are professional engineering, who know the engineering aspects, who can perhaps what you see on the right hand side, prepare a digital terrain model which is more useful for engineers. So that is why much of the the drone images which we got right at the beginning, the drone videos were prepared for those those photographers who were mainly for marriages and all. So they put a lot of fancy, or I would say exciting videos behind as a background to the drone videos. But I think much of the calculations analysis could not be done using those. So we got professional help from really good people who end up preparing nice what do you call it, terrain model, and we had an elevation profile at every 10-meter section along this stretch. So it's a huge chunk of data. And using this data, about 5 locations were identified. So these 5 locations where, you have this, right from the beginning, you have location 1. I will not probably rush through this small location because each and every location is unique. But you see from the photographs that much of this eye visual also will tell you that, this is the likely part. It says low system location. I hope you can hear me at the other end because I keep getting a warning on my screen that my resources are low.
Yes,
We
sir,
can
you
hear
are
you.
audible. Yep.
Okay, thank you. So, like I was saying, much of these images or photographs themselves will tell you, you don't need a rocket science to explain that so much of rock debris is there. So, likely path, this is the likely path. But you see, entire stretch has been documented, and you see that you have 2 separate slopes at 80 degree. You will see these numbers as I run through the next few slides. That is the number. You will see the stretch of the weak zone and the gradient of the top 80 degrees and down gradient. So you have a much steeper and a slightly shallow gradient. And therein, each photograph, you will also see these black lines, which are the railway tracks. So I'll run through them remaining, and these are something which you will see all together. That's the location 2. Similar to this, you have the railway tracks and the stretch is 50 meters. Location 3, and at several locations, we found that, rock debris was there, loose rock debris. Plus, you had some large pieces of rock which were probably, let me say, quote unquote, dying to fall down. At some locations, we also saw, rigid barriers, ISMB rigid barriers. What you see is they're pretty much damaged. Of course, it's then no rocket science again to tell you that rigid barriers are not a good thing because they cannot take first of all, they cannot take multiple impacts. And second, there is no, what do you call it? No, how do I put it? Your energy dissipation doesn't occur with them. So they are really, it's like, sitting a straight, what do you call it? A straight, rigid thing, which is, just sitting there to take all the blunt of the rockfall. So like this, we have one more location, again, a set of rigid barrier. In this case, you have a concrete barrier, which has again taken, extensive damage because of the rockfall events. I can go on because this is location 5. Incidentally, location 5 is where the 2017 train accident happened, the HTTV Hubli HTT Express. Therein you saw wherein even more accumulation of debris near the, what do you call it, the tunnel face. That's the mouth of the tunnel. So you're actually looking at the mouth of the tunnel from here. And what you see is there's several pieces, several debris, plus weak zones. You identify weak zones to each and every section. I'll skip this, go to the next one. So with all these mitigation systems which are seen, it was more important to see which is the most effective mitigation method. We try to group them into 3. So the first one is prevention. Prevention, you just do simple scaling, trimming of the, of the weak pieces, remove them. And if necessary, you do some short blast of shotcrete, which can be supported by rock anchors. The second one is a retention method. In retention method, you use mesh and netting, and with anchors, you support them with anchors. And the third one is you protect the your what do you call it, valuable infrastructure, or protect the system using ditches, sheds, or even flexible barriers. So what we needed for this site was a combination of two or more methods, and to see that which combination really helps more suitable. When I see the combination, we have I would say I feel that IRC 23 is special release 23 is an excellent code, because some find it not to be in depth that agreeable. There's no depth to it, but at least it really covers a wider zone, to wherein it helps to you can use it as a what you call it, first order of investigation, to see which kind of system or zone is more helpful. So this table has directly been copied, shamelessly been copied from the IRC. What you see is right from top to bottom on the right side, the cost goes high as you go down the table. That is true. So we start with the top one, which is most cost effective, and then go down, which is concrete rock sheds, which is highly expensive. In fact, for the information of the audience, we have this what do you call it? Most of these retention methods have been experimented with in the what do you call it, west coast of the Maharashtra west coast, wherein you can see near Mumbai, rock sheds are being used. I would say that's again for the first time. Your flexible barriers are there. We are using them. Yeah, in fact, I can say all the plus all the tradition methods. So we look all these 5 locations. I'll just speak about the 2 important ones, which is the first one, the secure drapery system, and the second is rockfall barriers, which were both of the. I'll briefly look at the design, just maybe rush through the slides, but more importantly, the conclusion or the findings from this design. There are other methods which were really again explored, especially the the gabion walls and the concrete. Concrete was discarded because of its again damage history, and gabion walls were not considered because of the large space required. So earth embankment and gabions were discounted. There's other method wherein you use shotcrete. The examples we saw that most of the shotcrete did not have enough reinforcement, but it's really well documented. At least most of the literature and the site and the experience we have seen is shotcrete works poorly when exposed to weather along the our Maharashtrian region, west coast. So it's again the durability is an issue, and also you can see separation of shotcrete from the from the wall or the rock face you want to protect. So the idea of having protecting the face against extreme weather dies off if such a separation starts in. So we needed something wherein the maintenance is minimum. So draped or mesh system, it has a design. I'll just not go through the design of this slide because of, again, I don't want to lose the interest of the audience, but I just thought maybe some of the important input which is necessary for the design. I'll just go to the next slide, which shows the input. So these are, what necessary, for you can design this to deduce what is the factor of safety, which is factor of safety in this case is kept fairly high because, your geotechnical data in this case is quite weak. So we wanted this so that the prediction in such a case, we wanted this to be more, on the safer side. Again, there is some complex geometry which cannot be accommodated in the design. And if there is any rockfall or debris which which is there within the system, it's again quite difficult to model this thing in your simplistic design, which just takes the system in just equilibrium when the mesh or the drapery system is anchored against the slope. So finally, we had this system wherein you had a system of steel composite wire mesh drapered along the weak zone. You also have a rockfall barrier, flexible barrier, and again, this description is available in IRC code. You can go through it just to examine this all the I think you will have a better view if you carefully examine the code and the why is it better? Because again, it's based on this a well-established or internationally recognized European standard ETAC 27, its design specification, which is again based on a lot of experimental data, a lot of back analysis, and it's a well-established system, I would say. And it's so most of the design is carried out either against the serviceability load or the ultimate load. So if you want to design against the ultimate load, of course, you would say that after maybe a few crashes, you need a complete replacement of your barrier system. And serviceability would mean that at least the safety factor against the impact load is against 3 or 4 times the energy which is really demanded by the falling rock debris. And these barriers range right up to 8,000 kilojoule. Let me tell you, 8,000 kilojoule is a massive, huge number. Even a few thousand kilojoule, it will dwarf you if you're standing next to it. And we also wanted that the barrier system, because of the flexibility of the barrier system, when some debris falls on it, there is elongation because it's flexible. It's designed to elongate so that the energy gets dissipated. And post elongation, there should be substantial distance or gap between the railway and the barrier. Okay. Its design again is quite simple. I would say it's a school level physics wherein you have the total kinetic energy of the falling block due to again the linear velocity and the angular velocity. You want to design this system so that entire energy gets transmitted to the foundation and it's dissipated in the ground. There's a very nice computer program. I really, appreciate it's of course a commercial program. We've tried it against, a standard DEM model wherein, you allow a block, but I think nothing compares this to it. So I would really appreciate the team which has gone behind in developing. Why so? Because if you look at this slide, it does not even look at single trajectory. It looks at multiple trajectory to get out the most probable, I would say, cause or probable extreme cause which can cause, which is readily for rockfall event. So each of these lines which you see, it tries to mimic how the energy or rockfall event happens, and every bounce shows how is the energy dissipated. Of course, there are several input, but the interface, I found it quite easy. You only allow minimum, minimum amount of, probability of, how many minimum bounces which can pass the barrier. So if that small thing is a barrier system, that's what you see, how much can pass through it. And you try to maintain this to be minimum, say about less than 5. In our case, we wanted to keep it as less than 2%. So just a case of one particular case, because I think we are going to show you an example of this 2000 kilojoule capacity. That's for one particular span or design. It was, done it. And it was very much in news after that. It says, although the bad tested, but it came, unfortunately did not, I would say the engineers who made a lot of effort in getting this thing done needed a proof, I would say, with the limitation budget given at that time. So a small, I would say, a pilot of the pilot study was funded of about 6 crore rupees, 6 crores or so, to fund one particular section. And when you go back and you see that out of those 5 sections, choosing the one extreme one and putting all your money, gamble money on that is something which, was merely a challenge. And Yeah, we had also experts going in. So I like to put this photograph over here because it was a holiday, and my wife and daughter, so they accompany me. This you see them sitting in this bunker. That's a railway engine sitting inside. So that's there. So experts went in to see that this thing goes in very well. Okay, July 23, a surprise, wherein this particular, I would say, pilot of the pilot study was used, was the only site in 2023 which got the impact of the, what you call it, the debris falling. Many would see this, as a failure. I see these photographs as success, because one thing is for sure, you did not anticipate this much amount of energy falling on the barrier system. This was beyond the design capacity. But despite that, a small section, a failing, but in compared to the larger section, what you see is the entire debris was held in. None of the debris allowed to fall down on the railway track. Board people were so, I would say, fascinated by this. Post 2023, railways have sanctioned special amount to be, cover for all the dangerous tracks along this entire stretch. So I'll just conclude this by two statements. One is, a single solution may not be sufficient to prevent any debris, to prevent the debris from damaging your infrastructure. And maintenance, it can be minimized, but it cannot be altogether be eliminated. So with this, I like to acknowledge the various people, cannot name them all, but especially railways, who some of them are who actually gave more than the due, I would say, the time for which they were paid, but gave sufficient more. And really, these are the people who went down to make this, I would say, the whole thing quite a success. With this, I like to stop and say thank you for listening.
Thank you, sir. Wonderfully presented. Thank you for the detailed presentation, very illustrative one. So moving on, I would like to mention again that we'll be having the Q&A session towards the end of all the presentations. So now moving on, we'll be starting with the second presentation for this evening, and it will be presented by Dr. Ratnakar R. Mahajan. So I would like to call upon Dr. Mahajan. Dr. Mahajan is alumnus of IIT Bombay and working as Regional Technical Manager at McAfee. He is responsible for India, Southeast Asia, and Pacific markets. He is a civil engineer with a key experience in soil reinforcement, ground improvement, retaining structures, slope stability, river training, channel lining, and rockfall protection solutions.
Very good evening to all of you. Sumit, I hope I am audible.
Yes, sir, you're audible.
Okay, thank you. So first of all, thank you Institute of Engineers and FIB for giving this platform. Also, I would like to thank Professor Ashish Juneja for accepting the request to be a panelist on this webinar series. I think your presentation has made my job very, very simple, because there are many things which you have just touched upon, and I think the audience will really love to just repeat of what you said through some of my slides. So with this, I would like to just mention I am working in a company which is present all across the globe, more than 130 countries, with 23 factories spread across the 5 different continents. Of course, McAfee India started its operation in 1998. Also, we have basically expanded our operations in construction through company McAfee Infrastructures Private Limited in 2019. And we are looking at India region as one region which includes Nepal and Bhutan operations, where Nepal started operations in 1995. Of course, we work in various areas like rockfall protection, snow barriers, erosion control, retaining walls, landscaping, floorings, fencings, ground improvement. You can visit our website to understand many other areas in which we are working. Today, I will be focusing on the rockfall protection works. Of course, first, what's this rockfall? Rockfall is a movement of rock mass along slope. Of course, it could be free falling, bouncing, rolling, or sliding. I want to just show you some videos from the YouTube which I collected so that you get an feel of an rockfall while watching this webinar. Of course, this is captured through a dash cam of a vehicle where you have seen, how exactly can how. This is from clipping from NDTV. So you see a landslide, that's happening. But of course, why I wanted to show landslide, this is another video which shows landslide. But before landslide, just observe here. See, here the rocks are falling. You can see here, the rocks are bouncing. You see the rock bouncing, coming down. Yeah, see the big, very big, very big. Okay, so this is how exactly the rockfall usually is initiated. If it is a site like what Professor presented with a nice rock of, let's say, basalt breccia, the failure would be different than the, let's say, in Himalayas where you have soil boulder mix, it could be different, Usually, the rockfall events, they basically starts at the top of the hill, which is typically a vertical, which is we call it as a detachment zone, and then they roll down. That's typically referred as a transit zone, and finally the runout zone. Of course, the big rockfalls can happen. Of course, is with where you have very big masses in the detachment zone. Okay, and the factors triggering this rockfall could be various. It could be vegetation, it could be rainfall, it could be avalanches, it could be drying and wetting cycle, or the presence of soft soil between the joints. And usually the detachment, when it happens, let's say from a vertical cliff, so it's going to be having a simple fall as a free fall. But if it is on a different slope angles, then you will have different motions, which could be basically a rolling motion, sliding motion, or bouncing, something like simple slide or maybe a bouncing one, Of course, the animations what I'm showing are the exaggerations, but typically these are the motions. Of course, why we need to understand this is in order to intercept these falling rocks, you will need to understand the mechanism, how it happens, and what are the different basically possibilities. At the bottom of the hill, you will have an area where you can say a runout zone where the large volume of the rocks can be accumulated. Usually, of course, when we approach for this rockfall, let's say mitigation or protection, of course, we'll need to understand what is the possible cause, of course, then what's the volume, because unless you are able to anticipate the volume, then you will not be able to design the solution. Of course, it is going to be a probabilistic analysis where you are going to estimate and then design for it. What's the possible course of the rocks that will be following from coming from the hill, and which are your targets, whether like Professor presented is a railway track or whether it is a road, whether it is a hydropower project, whether it is an building. Of course, depending on the type of target, the kind of risks what we are anticipating, accordingly the solution will be chosen. Of course, there are various kinds of solutions. This is a big list, but let's say you have protection measures, retention measures, and prevention measures, where I will take you through these measures one by one. Of course, one of the simplest and the safest option, the first is scaling, where you can just remove the boulders or debris, make the slope free of possible rock falls. However, there is a limitation to it. What's the volume of these loose rocks available, as well as what's the height, whether you are able to reach it, what is the property or infrastructure at the toe of the hill, whether we will be able to hold this loose scaling. The most simple one is bumps and benching. So you can have, let's say, a slope and you can create bench. There's a very popular technique which is being adopted. Of course, here you will need a lot of space, because if you have space, then you can have this bumps or benching. What exactly will happen is with these benches, the amount of energy the rock will bring along with it, that will be reduced. And of course, the amount, the protection what you are going to provide can be accordingly designed. Very simple. Higher the energy, higher the cost of the solution. The most commonly adopted solution is earth embankment, very cheaper one. However, the limitation is the space, like Professor mentioned. In the previous case, the earthen embankments were ruled out because there was no space available. But if you have space available, then you can definitely go for the solutions like the earthen embankments, like this, which can be built with simple earth or maybe a reinforced soil solution. So yeah, like reinforced soil or retaining walls, or let's say the embankment. You can have the rigid solutions also, like the concrete barriers, like the professor presented examples of concrete barriers adopted in the central railway area, where you have seen the kind of damage it can make. You can have masonry walls or timber shoulder pile walls. Of course, you may look for even reprofiling, resloping if you have possibilities of flattening the slopes. That's also there. Loose scaling, of course, like you have the let's say infrastructure to be protected, and there are loose rocks, so maybe probably stopping the traffic if it is railway road, or maybe providing a temporary protection measure and make the loose rocks or the debris to intentionally bring it down, which shall not cause the rockfall later on, but an intentional rockfall appear. Or you use very small charge and do the blastings. You can say a controlled blasting, where anticipate the overhangs and these overhangs can be removed. This is a photograph showing the loose scaling. Of course, for this kind of loose scaling, you will need a proper skilled, let's say, people with taking care of the safety, the volume of the mass, or let's say the rock, which need to be scaled down to be anticipated, and then it can be done. Of course, this is very cost-effective solution for immediate threats to be removed. However, this is not a guarantee that the rockfall will not happen. So we will need some protection measures, but this is one step. Here, of course, it could be dangerous situations if the geological or the site is not properly studied. The second solution is meshes, typically steel wire meshes. The steel wire meshes will prevent the rocks to exactly, let's say, coming down, or they can be contained in a certain area. Of course, in this case, the volume of, or the area to be covered by meshes will govern the cost of it. If it's very big area, it will be a very high cost. And looking at the site locations, accordingly, the solution can be chosen. Or the another solution is rockfall barriers. Sometimes it is referred as dynamic rockfall barriers, which can be installed on a slope. They are, let's say, relatively easy to install. Could be even economical solutions in case the volume or the surface area to be protected with meshes could be higher. However, of course, please keep in mind, any rockfall solution is not going to be maintenance free, because This is very important. I want to mention many times as a civil engineers, we design certain structures which are maintenance free. However, rockfall solutions are requiring the maintenance routinely, which will be depending on the kind of material it's coming. Of course, the limitation with these barriers could be the energy levels. If the energies are quite high, then the possible available rockfall barrier, then you will have to go for a different solution. That's the limitation. For very high energies, of course, you can go for the earthen embankments. It could be a conventional, simple earth embankment or reinforced soil structure. The advantage is it can take very high energies. Disadvantage is it requires a lot of space, but of course, this is very, very cost-effective solution. Alternatives could be you just build the tunnel, and avoid the area where you are having the rockfall. Of course, you can imagine the cost of building a tunnel could be very high, but that's also as an option. Or build an artificial tunnel, like you call it as a rock shed, which could be made of let's say, rigid materials. Like for an example, you can see here a concrete slab resting on the number of pillars, where any rocks coming from the top will be catered by the area here, and there will not be a threat posed to the people or the traffic below the rock shed. Of course, it's very, very costly. How to design them is not really so easy. Another challenge is if it is being to be constructed in hilly areas. Of course, the placement of the foundation of such a structure is going to be a challenging one, which could be like something like, if such a situation is there, then you will require very, very huge cost to build this kind of rigid structures, Or you can build a ditch or trench in case you have space. You construct a big trench where the accumulated debris can be collected here. Again, this is a very good solution. However, subjected to the space availability. Sometimes you may use the shotcrete, like you place a mesh on the rock slope and put a shotcrete. However, one of the limitations of the shotcrete, like Professor presented in the case, like the mesh is getting separated from the rock. Sometimes these hills, you have a lot of subsurface flow, and with this shotcrete, you just stop the complete movement of the subsurface flow, which leads to pore water pressure generation and possible failures. Of course, it's a good solution, but of course not so environment friendly compared to, let's say, carbon footprint, if we want to compare. However, this is one of the good solutions to be adopted with certain cautions. Very important part is drainage. Many a times is being observed. The rockfalls are being noticed in the monsoon areas. That's related to you have very highly fractured rocks, jointed rocks, from where the water seeps in. You have very fine material accumulated there because of weathering, and it creates a nice smooth surface where the rocks can just slip on, and then you can have the possibilities of rockfall. So drainage is very important, which can be typically built using, let's say, drilling holes, and through that holes you can put the perforated pipes. And many times I get a question, are you really sure it's going to work? Just to show you, this is one of the project on the Mumbai-Pune Expressway near Adoshi Tunnel. These are the pipes that's being drilled in the hill, and you can see the amount of water it drains off during the monsoons, and around the year, a lot of water comes from there. Of course, when we design the rockfall solution, of course, we need to understand the detachment zone, from where we are going to understand what's the dimension and position of this detachment zone. Of course, this directly impact the economy of the solution. Second is the morphology and geology, especially how it's going to influence, and basically the type of work what we want to use will be governed by this. Very, very important part, accessibility. As I said, you can really look for this scaling operation, but if the hills are very high, like typically, let's say, in Himalayas, you have inaccessible tops, or let's say even other areas where you have inaccessible tops, then you cannot do anything. If that's the case, then of course you will have to see a feasibility of any solution to be provided there, which you want to hold the rocks there. The volume, of course, as I said, volume will govern you the kind of solution you want to choose. whether other than embankment, barriers, or meshes. And of course, the economy also will be governed by that. And most important part, what's the value of target, what you want to protect. Accordingly, of course, you will have to take care of the solution. Now, when we look at these rockfall protection works, the simplest one is you put a mesh. The mesh could be simple double twisted mesh or the double twisted mesh reinforced with the steel wire ropes, depending on the situation. But the most preferred one is the double twisted wire mesh, that is the hexagonal wire mesh with the wire ropes. Usually, of course, what you need to understand, of course, we are going to put a mesh facing with the longitudinal ropes on the top, and the mesh will be anchored at the top so that you have the rocks which are coming down, and then of course at the bottom of the hill you can have specifically a trench, or you can have a steel wire ropes which is being used to hold anchors, and additional wire rope at the bottom which can help to accumulate the debris at bottom. Of course, let's look at an animation. Of course, this is an exaggeration. Of course, the mesh cannot be just in air. What you see in the sketch, it will be actually hugging the surface. But just to give an idea, usually if you have a rock slope with the mesh and you have a detachment, so of course it will come down with the mesh. The falling rocks will be guided, and they will be guided at the toe, either with the trench at the toe or maybe with an anchor at the toe, something like this, and you will have accumulation of the debris. So accordingly, the debris or the debris system to be designed, which will be dependent on the volume of material to be retained at the bottom, the kind of mass it's going to be there. Another option, typically we refer it as a secured drapery. Secured drapery is nothing but where you put number of anchors, could be the soil anchor or rock anchors. Here, of course, you are having a mesh followed by number of anchors all along the slope, and then of course the cables, nets, or ropes which are being placed. So the idea is to possibly avoid the detachment of the rock mass from the slope, and the detached rock mass, if it is there, that's get retained in the mesh itself. So the mesh will be designed for a volume of the expected or anticipated or assumed rock mass between the rock nails. So just to get an idea how exactly this could be, a photograph showing a steel wire mesh being installed with anchors, and that's being reinforced with the external cables, or you can have the additional meshes in that. Or let's say a part of the rock mass on a slope is expected to detach, then of course you can have number of nails or anchors. Here you will have to understand the behavior of mesh, how exactly the mesh will behave, especially when you have such kind of situations of rock mass movement or accumulation of debris at top, so that you understand how much a punch force, because it's a punching kind of force, it can take, and how much could be the deformation. Obviously, when you have the drapery mesh installed on slope, looking at simple drapery or the secure drapery, you will need to understand the tensile strength of the mesh, which can be tested as per the various ISO norms. I don't have to go in the details of this, but that's how exactly you will characterize. Just to give an idea of, let's say, one side, we are looking at vertical cuts for a railway project. That's from the northeast part of the country. Here, during construction, large quantities of rocks were cut where blasting was done. Of course, there is a lot of fragmented rock on the surface, which poses a threat to the safety, I would say, of a running railway line. This is a railway station where exactly near close here it's happening. So here the solution, of course, was like placement of a mesh, and of course the nails, what we just seen as a secure drapery system. Of course, here first step is you have the anchors at the top. Of course, the anchor design will be governed by the type of rock available there, and then you do the proper installation of anchors followed by installation of the drapery system. Of course, while doing so, proper care, safety has to be done. According to the rock size, estimated amount of volume, you choose the different types of mesh. Like it can be a simple hexagonal wire mesh, or you can have the steel wire rope panels, typically what we refer as the HEA panel, high energy absorption panels, or you may have steel wire mesh reinforced with the panels, which we call it as a MAC armor system. So this is the photograph showing the construction of the protection while even the railway line is operational. So even these solutions are very, very flexible, not just from the deformation point of view, even from the installation point of view. You don't have to even, depending on the project requirement, you can continue the operations also. So this is like the high energy absorption panels. Another solution is typically a barriers. Of course, the function of barrier is to stop the motion of the boulder, catch it. Sometimes it is referred as a catch fence. Some people refer as a dynamic rockfall barrier, where of course you, let's say, anticipate an infrastructure, could be railway, could be house, could be road, and then of course a falling rock coming from the slope, which could hit the infrastructure and maybe there are damages. So you just install the barrier with the first, of course, is the foundation, followed by the post, upslope anchors, and then the interception mesh. And of course, if there is a rock fall, then the falling rock is catched or caught by the barrier. Usually, when you design these rockfall barriers, you need to take care of energy, but very important part is also the amount of deformations what you are expected, how far the infrastructure is from there. If it is very close, let's say you have road or railway very close here, you will have to minimize the deformations here. So there, the design of barrier will come, which will require the information on the deformation of the barrier. And what Professor exactly mentioned in the previous presentation, that these barriers are tested as per certain guidelines, that the European guidelines. There are the proper tests to be carried out, where this whole system is referred as a one system: foundation, post, rope, upslope rope, the brakes, and the mesh. That's to be taken care. So that's what typically referred as the EAD, European Assessment Document, which gives the information of these barriers. And usually the concept of this design of these barriers is these barriers are designed for multiple impacts. Of course, what are the main parts of these barriers? Are first, of course, nothing but the post. Posts are the vertical steel members which are installed, followed by the ropes, which are usually the side ropes, the top rope, upslope anchors, bottom ropes, and then the interception mesh, followed by the brakes. So this is a typical sketch. Let's look through the pictures. So this is a photograph of the barrier where you have a post, and then here you have the ropes which holds the post in together. This is basically an interception mesh. So there are possibilities of various types of interception mesh, like the rings. You can have the double twisted hexagonal wire mesh. You can have the steel rope cables. Depending on the energy, the different types of screens are used or the meshes are used. And then the brakes. So brakes like the omega shape brakes. The title of this webinar is Advanced Flexible Solutions for the Rockfall Protection Works. So if you have very rigid barriers, they usually get damaged. They cannot absorb the energy. Whereas these are the dynamic flexible barriers. They, per function of the brakes, are basically control the loads on the barrier as well as going on the foundation, which optimizes the overall solution. Of course, for designing this kind of barriers, you need to understand the kinetic energy, which is half mv square. That's the simple from the physics you can understand. And of course, when you design the rockfall barriers, you need to understand the kinetic energy, which is accepted approach for designing these barriers. Of course, you will have to design the barriers considering the deformations for the designated dissipation energy. The performance of the brakes is very, very important. And then, of course, the each and every element of the barrier, what I explained earlier, if does a certain function, and the whole barrier need to be considered as a one package. Another part is to be seen as the residual height. What it means is you design the barrier for certain height, but after the first impact, there will be a reduction in the height of the barrier. That's the remaining height will be referred as the residual height. And then you take a ratio of this residual height to the original height, and you basically classify the barrier as the different classification class ADC. So this is an example of a barrier which is installed on the Mumbai-Pune Expressway. Here you can see the post. This is the interception screen of the rings. These are the upslope ropes with the brakes. Same project where you can see the white dots on the black surface. These are nothing but the rock anchors, and the vertical ropes. What you are seeing is basically you have the high energy absorption panels that are being installed. So this is a secure kind of drapery system with a barrier on top. So with this barrier on top, you avoid providing a mesh on the top, and you economize the or optimize the solution. Of course, these dynamic barriers can be installed on various geometries, like this is a photograph where you have nearly vertical cliff and the barriers are installed with a post, let's say, perpendicular to the rock slope. Of course, while designing these kind of solutions, you will need to understand the size, of course, that is based on the geological studies, looking at the dip joints, looking at the spacing between the joints, looking at the understanding the local geology, morphology of the slope, what are the let's say the overall geometry, and then assuming certain parameters and then design it. Of course, for designing this kind of structures, you will require to design the anchors or nails. For that, of course, you can use the commercially available softwares like Slide. Of course, we have our own software, Macro 1, Macro 2, for designing various systems like drapery systems of simple and the secure drapery. For design of the rockfall barrier, you need to have a simulation of the rockfall, which is usually done by rock science software of Rockfall. With the combination of various softwares, you can design the overall solution. Now, I would just quickly glance through some case histories so that you get a feel of whatever we have talked about. So this is a first case history from Maharashtra, where basically PWD Maharashtra proposed to protect the temple of goddess Saptashringi Devi, where there is a nearly vertical cliffs. The height of the cliff was around 200 meters, and it was necessary to protect the temple against the rockfall. In the past, number of rockfall incidences were recorded. Just to give you an idea, at this temple, around 5 to 6 lakh devotees visit this temple, So it's approximately, more than 300 to 500 people visit every day. Of course, here the challenge was the extent of area protected was very big. The heights were very high, around 250 meters, 200 to 250 meters from the accessible location. During monsoon, there are clouds, so visibility is a challenge one. Here, there were vertical cliffs, and the hill itself was inaccessible. So the first time in India, the helicopters were employed for the transportation of the material. The site was such that even the regular civil construction workers cannot work here. So climbers, specialized climbers were engaged here. The solution was provided with a secure drapery system of high energy absorption panel, which is made up of steel wire ropes. And then dynamic rockfall barrier of 5,000 kilojoule capacity was installed of a height of around 7 meter. That was protecting around 150 meter length. So these are the photographs of the construction work. So you can see it starting from here, transportation of the interception mesh of the rockfall barrier using the helicopter. Of course, here very trained, let's say the manpower was required. You can see flying of this helicopter very close to the cliff. Installation of this post on such a steep cliff required the specialized expertise. Installation of anchors, you can see here. So safety is again very, very important part. And this is the marking of the top anchors where the secure drapery will be held on at the top of the head. So this is like the site where you can see here secure drapery of the high energy absorption panels. Here the dynamic rockfall barrier of 5,000 kilojoules, 7 meter high, around 150 meter length. Okay. And again, the success part of this, after this installation of this solution in 2015, December 2015, a rockfall event was reported on a slope above the temple in the month of June 2017. You know, June is typically a monsoon month there. And here the dynamic rockfall barrier captures these rocks which were weighing around 300 kg. And when this event happened, there were devotees just below these barriers, and the rockfall barriers saved this precious human life. So that's, you know, the success of this implementation of this rockfall solution. The another solution from Mumbai area, Gilbert Hill. Gilbert Hill is very interesting site. Just to understand, this is a unique site in India where the columns of hexagonal cross section of this basaltic lava are being noticed, which are around 65 million years ago. This is grade 2 type of heritage structure declared by the Municipal Corporation of Greater Mumbai in 2007. This area had a history of rockfall, and of course in this area there are residential complexes. Because of this adverse geological conditions, you know, it was required to provide a solution. There were some unscientific excavations which lead to instability of this hill rock mass, you know. Another challenge here was the steep slopes, no approach road to the execution activities, and large extents of area to be provided. Considering these space restrictions, you know, basically a secured drapery system was installed with HEA panels and steel grid. Here, of course, the provision of subsurface drainage was being taken into consideration to avoid the seepage issues, which could lead to a huge failures in future. So these are the photographs of execution. You can see here installation of the secured drapery. The white dots, what you see, are the anchors that's being installed, and this is like the people installing the mesh. You know, these are the HEA panels. This is the drilling in progress, and this is the finished one. The next case history from Mumbai-Pune Expressway, Borghat section of Mumbai-Pune Expressway. Here, basically, of course, this is a part of the Western Ghats, Sahyadri Mountains. Here, a tunnel is being built, and near the tunnel, there have been the incidences reported of rockfall and landslide. Of course, there are possibilities of damage to the infrastructure. So here, the solution was provided with the rockfall barriers of different capacities like 2000 kilojoule to 5000 kilojoule. Here, the nails were installed of 32 mm dia. Subsurface drainage, as I mentioned, drainage is very important part that were being installed using a PVC pipe wrapped in a non-woven geotextile. And some portions, where the slope protection were required with some vegetation, the mat edges, that is a high strength mesh with the synthetic mats were being installed. And these are the execution photos of protection of the slope with the barriers installed on the top. This is another view, another location where the barriers are installed. So if you travel from Pune to Mumbai, you will notice this solution being implemented. Moving from Maharashtra to the Himalayas, this is a project from Uttarakhand. This is for at hydroelectric power station, Dhauli Ganga. Here the issue was basically the fractured weathered rock with, of course, vegetation on slope. Due to the possible accumulation of the debris as well as the steepness, and combined with the rainfall, anticipated detachments of the rock mass in the upslip where uphill slope was anticipated. Here, of course, as usual, inaccessible location was the challenge and steep slope. So here the solution was provided with the dynamic rockfall barriers of 3000 kilojoule with 5-meter height. Typically, the length were around 40 and 80 meters at a height of 55 and 75 meter above the road level to mitigate the risk of rock detachment. These are the photographs during execution. You can see here the posts are installed, and the workers are now connecting the post with the ropes and the installation of the interception mesh. That's how this looks. From Himalayas coming to extreme south, this is Southwestern Railway in Tamil Nadu. Here, an incident was reported of a detachment of the rock on the railway line, so it was required to install the Rockfall barriers. Here, multiple lines of Rockfall barriers of 1500 kilojoule. Of course, I will not go in design and too much details of this. In view of the limited time, I will just present these case histories, and of course, we can interact. You can get in touch for understanding more. But most important part is you can have various kinds of solutions like rockfall barriers, drapery meshes, the embankments. So like this is showing the execution, but always rockfall protection works require specialized installation. That's why it makes so special work. Another example of from the Uttarakhand. This is at Lamgarh. Lamgarh is a landslide area. Here, looking at the volume of material sliding down and the space available, reinforced soil structure was used to build a rockfall embankment at the toe of the hill, where the Gabion fascia was a fascia, but this is a reinforced soil structure. And just to give an idea from this is a retaining wall of paramesh being provided for the road retention. The space was available. So here, this wall is approximately 10 meter high. This wall is around 40 plus meter high. So here the rockfall embankment was provided with the stone fascia paramesh system, so that any rocks and debris sliding down will be stopped by this rockfall embankment coming on the road, so that you have a safety of road being maintained. There's another project from the Himalayas, but of course a different state, Himachal Pradesh. This is a Pangi Nala, where the problems were observed of detachment of this the debris from the slope. The hillside is around 1 kilometer, you can imagine. Of course, the valley is around 60 meter deep with steep slope angle of 60 to 80 degrees. So very, very challenging site, inaccessible location, no approach road at all. Here the solution was provided of rockfall dynamic barrier, because you can imagine such a high slope, you cannot have the draperies being installed. The nice solution would be the dynamic rockfall barriers of 2000 to 5000 kilojoule. And some locations that's on the slope itself, the high strength mesh, that is steel grid HR30, was installed with the erosion control mat with let's say a biodegradable materials. These are the photographs of the barriers. Like you can see, there's a 5000 kilojoule barrier being installed, and on the slope the steel grid HR with the slope anchors and the biodegradable mat was installed. This is another site from Uttarakhand, Helang. Again, here the issues of exposed rock, which is, you can see from the photograph, it's completely fractured, surfacial instability, erosion control is a problem. So here a simple drapery mesh was provided along with the HA panels, and rockfall barrier of 100 kilojoules. So you can see very small capacity, that's 100 kilojoule, and then we are talking of 5000, 3000 kilojoule capacity. So this is like photograph of before the slope, and this is after installation of the drapery system and the barrier. Okay, this is Goltir. Okay, again typical Himalayan site in Uttarakhand, where a dynamic barrier of 1500 kilojoule capacity was installed. In a summary, you will need to have site-specific designs. Of course, understanding, as I said, this is a probabilistic design, anticipate and design. Here you will require multidisciplinary approach. It will not be pure geotechnical, but you will need an expert geologist on this project to understand the geology. Risk assessment, which will be governed by the kind of infrastructure you want to protect. Most important part, maintenance has to be considered for providing the solution or considering the solution. Of course, the codal guidelines, like Professor mentioned, IRC SR23, that can be referred. Drainage is very, very important part and an inevitable part, and I think must be considered as a part of another rockfall solution. Before I conclude, I would just like to say we have a design platform. E-design platform covers the various softwares available for, let's say, design of the flexible fascia and the soil nails. That's MAC design. We have ground improvement solutions. That's with the MAC bars, where you can design geosynthetics On the soft soils, you have MACRA river analysis for typical river analysis, MacTube design, that's basically a geotextile tube design. And very soon we are coming with our Rockfall softwares on the same design platform. With this, thank you very much. We will have a question and answer at the end of the presentation.
Thank you, Dr. Ratnakar. Thank you for the vibrant presentation that we have. And now quickly, we'll be hopping on to our third session of today's evening. And after this, we'll be having a Q&A session. And again, I would like to mention that we'll be having a feedback form in the chat. We request everyone to attend that. So now this session will be presented by Mr. Luca Gobin, and we would like to invite him. Mr. Luca Gobin is working as a corporate Rockfall technical specialist with extensive global experience in designing and implementing solutions for rockfall mitigation, slope stabilization, and managing slides and debris flows. He holds master's and bachelor's degree from University of Padova, Italy, and specializes in building preservation and restoration. With a strong focus on overseeing projects from design to construction, Mr. Gobin ensures technical precision and cost-effective solution. So we'll have this presentation on IoT revolution. So, Mr. Luca, you can start.
Yeah, thank you. Sorry, I was trying to activate my mic. So hello, everybody, and thank you for joining this webinar. As mentioned before, my name is Luca Gobin. I am the Rockfall technical specialist for Macaferri Corporate. So I'm based in Italy. And today I will introduce our smart rockfall protection using the Elomac geosystem. Okay. As Dr. Ratnakar was mentioning before, in our history, we've always been focused on reducing risk through the creation and innovation of cutting-edge solutions, like the one presented by him for rockfall protections. But we as Macaferri, we try to make a step further to that, because the goal is not only to protect, but also to have everything let's say, to have the knowledge of our systems, how they are on real time. Okay, if something is happening or something is impacting our systems, and then if some events are happening. So together with NESA, a company part of Macaferri Group, we are taking a big step forward, as I said, by adding IoT technologies to our protection systems. And today, more focus on rockfall protection systems, such as rockfall barriers or simple or secure draperies, as presented by Dr. Ratnakar before. This new direction not only aims to improve our technical proposals, but also ensures that we are always up to date with an evolving technological environment. This is our focus. This is our everyday commitment. Okay. During this webinar, we will explore this system, and this our new system, as I said. I hope all of you are listening me very well. Anyway, so just a brief introduction about the agenda for today. The topics we will cover today, with at the end, as we mentioned before, a Q&A session. So if you have any question, please type in the chat box, and I think we will go through at the end of the webinar. So first of all, I would like to start introducing the problem, okay, from where we started in developing. All our solutions, not only the other system that I'm presenting now, the IoT solutions, but also all the systems that Dr. Ratnakar presented before. So all the protection systems. The problem, as I said, the problem is the natural hazards, okay, and then the climate-related disasters that are substantially increasing, as we see every day in the past years. Just for your info, a couple of numbers in the last 20 years, they are doubled compared to the past 20 years, due to, as we see every day on the news, the climate change that has a considerable impact on these statistics, and then, of course, on these problems. And then the mitigation must be for us a priority. Actually, it's a priority for us as Macaferri for reducing the risk. That is, and this is, as I said, for reducing the risk for our communities. That is, as I said, as Macaferri, our everyday commitment. One of the solutions for mitigating the risk is investing in the digitalization. That is also what recently stated also the Secretary of the United Nations. This, according to the United Nations Office for Disaster Risk Reduction, the UNDRR, early warnings given 24 hours in advance can reduce the resulting damage by 30%. And by the way, for who is not familiar, the definition of early warning system, EWS, is a complete system that identifies potential threats and provides timely information to reduce the impact of these threats. This includes also monitoring, analysis, and communication of the risk to ensure proactive measures that can be taken to protect assets and ensure safety. From an investment perspective, the value of early warning systems is also clear, as we can see here in these statistics as well. So $800 million in early warning systems in developing countries can prevent losses ranging from $3 billion US dollars to $16 billion US dollars this per year. These data points show how important timely information and proactive measures are in reducing risks, and also prove the economic value of early warning systems as a strategic investment. This is why, with a clear understanding of the importance and the impact of early warning systems in the world, Macaferri has decided to invest not only in the solution that we saw before, protecting, but also in developing the know-how for applying the early warning system to the core solutions of Macaferri's portfolio, creating what we call the ELOMAC series. Okay, so Geo, Hydro, Eco, Infra, and Snow. So here we have a nice picture for a quick overview of all the possible application of ELOMAC series to our core solutions. Again, for whom are not familiar with our core solutions, we scroll quickly all the solution and also all the fields where we can apply our ELOMAC. So let's go quickly through all of them, starting from ELOMAC Infra, developed for infrastructures, that's why infra, such as tunneling and fencing. For example, for detecting the intrusion of wildlife along highways, or to install inside the tunnels. Then, sorry, we have also Elomac Hydro for hydraulic applications and solutions such as gabions. This year we celebrated the 130th anniversary, and Rhino matrices that are where we started, okay, 140 years ago. Then we are in the process of launching also Elomac Eco, specifically designed to provide comprehensive monitoring and management on various environmental parameters, such as the quality of the air, water, for solutions like, for example, landfills. Okay, so several number of solutions to, as I said, to monitor landfills, for example. And then Elomac Snow, that is designed for the advanced monitoring in mountain areas where there is a risk of snow avalanches. Okay, like in the Himalaya area, as we were mentioning before. And then last but not least, we have the Elomac Geo, okay, aimed to reducing the risks for of rockfall events, and then providing the required level of safety to both infrastructures and communities. That is the let's say the topic for today. So here we have a nice overview of possible applications to our rockfall mitigation systems, such as rockfall barriers, simple and or circular draperies, soil nailing, and etc. etc. Okay, so finally, we can see how our Elomac looks like. And then let's discover all the main features of it. So first of all, it's as you can see from the picture, it's a disc-shaped device made of a metallic alloy, aluminum and ergal, for resisting to impacts. Okay, because it will be installed, for example, on rockfall barriers, and equipped with 8 tie rods that we call them in jargon legs. Okay, for the connection of Elomac to the solution, and then one antenna for communicating the signals. Elomac is very small. Okay, approximately 30 centimeters by 60 centimeters, and with a very limited weight, approximately 8 kilos. That means that is very easy to be handled by workers and carry on site. That are typically sites, job sites for this kind of application, for rockfall application, are typically located in remote areas, no? So it's very difficult to access and to reach. It's also extremely easy to install, and then skilled workers are not required at all. In fact, not even wiring operations are needed for the installation, because it is powered by standard batteries with a guaranteed lifespan of minimum 5 years. And then also maintenance is very, very small or not needed in that few years, that 5 years, unless impacts or problems in the with the solution. With the protection installed. So the alarm signal can be notified using either the satellite, okay, or the GSM 4G networks, ensuring the full coverage all around the world. Also, as I said, in remote areas where there is no signal at all, in that case, we can install Elomac using the satellite, so the Iridium technology. The notification time depends on several factors, as you can easily understand, such as the location, the coverage, the type of connection that you have chosen for the Elomac for that specific location, etc., etc. But we guarantee the notification within 3 minutes. Again, this is the maximum time that you can expect. But for example, in accessible areas with very well covered and using 4G or GSM network connection, this time can sensitively drop to within 1 minute, not even 1 minute. Okay. And the alert is notified, so the alert signal is notified directly on the app, okay, so on your device, or with an actually and with an SMS, so a short message system, and also on the email, or you can check it directly on the browser on the dedicated page. The app is available on the App Store for Apple and for Android too. With the app, it's possible to monitor the protection system and the Elomac on real time and from everywhere you are. As I said before, directly on your device, okay, laptop, yes, but phone, I mean, smartphone or on the tablet. The goal of this new technology is of the digitalization and then of Elomac is to make people and our communities safer, as I mentioned before, okay, like we saw before in the preview in the first couple of slides. And how could it be done? Installing Elomac on different applications and solutions with a smartification of each of them. So let's go more in details for each of these applications. First of all, turning our Rockfall and debris flow barriers into smart barrier systems. Installing Elomac Geo directly on our barriers, as you can see here in this render, in this example. For detecting the impacts and then the triggers on real time and on 8 different locations, as you can see the small points in the slide. 8 different locations for each device. 1 location per leg, remember the tie rod we showed before, and each location can be set with a different threshold, and of course is sending a different alarm to the app. Here we have a nice case history, a nice installation recently done on a barrier in Italy. Okay, on a RB3000, that is a 3000 kilojoule energy level barrier. And we installed 8 Elomac Geo directly, each of them installed directly on the post, as you can see on the slide here. I don't know if you can see my pointer. And each device is used to alert to span of each barrier to cover the 1,675 square meter of barrier. And then Elomac Geo can be installed on drapery systems such as simple draperies and secure draperies, as you can see in this render. Okay. Also in this case, the goal is the smartification of our drapery systems meant to contain the material detaching from unstable slopes, as also mentioned by Dr. Ratnakar before. This is the goal of our drapery systems, and the goal of Elomac Geo is to alert the drapery systems and then to make them smart. So detecting in this way movements and detachments all along the drapery systems, so along the slopes covered by our netting systems. Here we have an example of a recent installation on a secure drapery realized with HA panels that are our rope panels, okay, Macaferris rope panels. Again, this is another nice picture of this job recently installed and the Elomac Geo was installed on a specific area that was needed to be alerted. See, on the specific rocks that are expecting to move, no? So at least we want to alert. Elomac Geo can be installed also on existing barriers, not only on new barriers or new systems with a specific retrofitting. This means that we are able to adjust our Elomac Geo to Rockfall protection systems already existing for adapting this system to the new requirements and standards, because this is actually most likely in Europe this is the goal in the future. They are already working on new guidelines and standards to make as like a law that must be required by law, that all the systems they will be let's say smart, okay, with install an IoT to have everything under control on real time. This is actually the next step for the European standard, next in the short period, so then the next just couple of years. So in this way, we are going to make also the all the systems, all the protection systems smart, in a kind of I like to call it an update, no, of the system. The same way you update your iOS on your smartphone. Again, here another recent another installation. For example, we recently installed Elomac Geo devices on Rockfall and debris flow barriers already. I mean, installed previously. We installed 43 devices, Elomac Geo devices, on EPFM 5000, so a 5000 kilojoule energy level barrier, and also on different debris flow barriers on the same site. Another possible application for Elomac Geo can be for example, for the job stability monitoring. It means to install Elomac Geo for assessing and managing the risks of unstable slopes. Elomac Geo, in fact, can be installed and integrated with complementary components such as strain gauges, inclinometers, sirens, signals, and others. Here again, I always like to show also some application, okay, real application. In this case, Elomac Geo devices have been installed connected directly to some blocks along the channel. also as we saw before in the previous slide, for detecting and monitoring possible debris flow events. So not only installed on the protection systems, but also on site, okay, for detecting the events to make them as a early warning system. In this picture, we have another detail of this installation installed in north of Italy. And then I want to stress again our effort in innovating and improving our solutions. And this effort didn't stop with Elomac. We developed several additional kits with complementary components that can be integrated with Elomac Geo for upgrading our system, making it plus. In this way, we will be able to have all the info and data needed in one single system. So in one app, in one hand, I would say, directly on your device. So smartphone, tablet, as we saw before, etc., etc. This is here we in this slide we have the list of available kits that can be integrated with Elomac Geo for adding info and data and increasing the level of detail for the smart system and then for the location of the project required. Starting from rock displacement control kit, meant to measure displacement and detect movements, for example, with strain gauges. And then slope displacement control kit for monitoring for example, landslides. Then climate control that with this kit, the kit is meant to monitor the environmental conditions with components such as rain gauge. Groundwater level control kit for monitoring the variations of water level. Then the stability control kit for monitoring the movements of slip surfaces, for example, using an inclinometer. And then wind control kit for detecting the wind conditions, intensity, direction, etc., etc. And then last but not the least, the alert control kit that consists of additional components for alerting and reporting the events directly on site, so not notified on the app. Okay, so on parallel, of course, it's notified on the app, but with these additional components, we are able to notify directly on site the event, that the event is happening, okay, the alert, with the devices such as you can see in the slide, sirens, gates, signs, directly connected to the Elomac. In this way, you will have everything, everything, so monitoring and also alerting, everything I show you till now, everything in one single system, avoiding additional costs, for example, and everything wireless and on screen live directly on your app, on your tablet, on your smartphone, on the browser if you have a laptop, and also on site, considering the additional components that we saw before, the alert kit. I see maybe we have a couple of minutes just to show you some additional pictures that I always, in my opinion, are better than a lot of words, no? They explain better the system. This is let's say here you can see the road. This is a road on the border between Italy and France, and this is a very nice chute in French, but so it's a corridor, and this is let's say a gully, okay. where we install, you can see here all the barriers. Maybe it's small, but maybe I hope you can see all the lines of barrier installed. And for each barrier, for each line of barriers, we install different number of devices, of allomatic geo devices, calibrated at cell, service energy level, and MEL, maximum energy level, that are the two main, let's say, levels for Rockfall barriers. Again, for whom are not familiar, when you test a barrier, when you design a barrier, you design a barrier at cell or at MEL. Okay, so service energy level, for example, for a 3000 kilojoule barrier, cell, it means it's 1/3 of the MEL. So for the 3000 kilojoule energy level barrier, it means that cell it's 1000, at MEL it's 3000. It means that the barrier is meant to stop one impact at 3000 kilojoule barrier, or several impacts at 1000 kilojoule at 1000 kilojoule energy impacts. See, I mean, here you see we install a total of 18 Ellomac, okay, with different thresholds of activation, okay, depending on how closer we are to the road. So a nice picture of the installation with the Ellomac you can see here installed on PFM. This is a 5000 kilojoule barrier. It's installed directly on the post, and the signal, the traffic light and the signal are connected directly to the Ellomac. So if an impact is happening, see the road connected to the impact panel. So if something is happening along the gully, the road is interrupted by the traffic light, and then also by the signal where it's explained that something is happening. Here, a nice picture in Italy of Ellomac Geo installed on secure drapery, still HA panels, so our rope panels. Okay. So you can see now the cliff, how steep and dangerous looks like. And one Ellomac was installed there, so if movements are happening, the alert is sent. Actually, there is also I think an inclinometer installed here just to check the movements. And then another case history, another case study in Italy of several Ellomac. You see the dots installed along a Rockfall barrier, on Rockfall barriers along a road, okay, a national road. Here you can see the Ellomac installed on the post. And then last, we already had a quick overview of this case history, but because I didn't want to spoiler the kits, here you can see actually the Ellomac installed on the boulder to detect the debris flow, possible debris flow events along the channels. But connected to the Ellomac, we have also a meteorological station and also a sign with the light. Okay, I think that today from my side that's it. But of course, if you need any additional details, please contact us or our organization based in India. Now I think it's the turn of the we can start the Q&A. So if you have any questions, please write them in the chat box, I think, and we will answer right away. Thank you very much.
Thank you, Mr. Goppin. The presentation was really nice and interactive. And now we are just on the Q&A session. Due to paucity of time, we'll take a couple of questions, and we'll start with the IoT section only, the Hello Mac one. So the first question is for you, Mr. Luca. Question is, do the weather condition influence the frequency and severity of rockfalls?
I think you mean on the notification of the alert more than Rockfall.
Yes.
I mean,
Yes, exactly. Yeah.
I mean, it influences, of course, also Rockfall events, but no, so the system is meant to send several messages, so with a redundant. In a redundant way in order to do not, I mean, in this way we don't lose any track also if severe meteorological conditions.
Okay. Thank you for the answer. So we'll take another question, and it is again on the Hello Mac. So this question is from Mr. Surinder Rana, and first is his comment. I think the Vanid people have been saved if this system have been they are including Hello Mac for warning. Of course, this is the smart alert system that we have, and this would definitely have benefited. So, and the next question from him is in terms of the corrosion. So, design life as far as corrosion is concerned.
Okay, so as I said, the system is with is produced is manufactured with you call it an alloy, okay, a metallic alloy of ergal and so a metallic alloy that is meant to prevent the corrosion. So we don't also we install them in Norway under snow. We install them in Asia, for example, in Southeast Asian, in Hong Kong, in other, and we never experience any corrosion because, as I said, and as I mentioned before, the disc, the metallic disc is built, is manufactured with this alloy that resists to corrosion.
Okay, thank you. So we have another question for Mr. Luca Gobin, and he says, Mr. Luca Gobin, what is the primary purpose of using IoT in detecting rockfall and environmental hazards?
What is this? Sorry, say it again because
What is the primary purpose of using IoT in detecting rockfall and environmental hazards?
So the idea is to, as I said before, to have a prompt answer, a prompt intervention during or after the event. Sometimes we don't have track of that unless it's too late, and then as I showed before, sometimes you need to close the roads, in tempestively, so immediately. Sometimes this is the goal of early warning systems, is to increase the level of protection to communities, because in this way we know what is happening and if we need to make an intervention to alert. This is the idea. Sometimes these systems are, I would say, most of the time, but are installed in remote areas and not to have a track or to know that something is happening, it's very, very tough, or like to at least to have to have track of this in a short time that is needed for reducing the damages, okay, to people and to infrastructures. Also, sorry, I want to add that the regarding the previous question, that the disc, it's an alloy of aluminium and ergal. So I'm not like a material engineer, but it's very resistant to corrosion. Aluminum, say it's corrosion free, but that's the okay.
Thank
So
you.
if you have another question.
Yeah, so we have our another question, and the question is from Mr. Chinnasamy Krishnan. Question is for Dr. Ratnakar Mahajan. What is the maximum kilojoules to be considered for designing of rockfall mitigation?
So first of all, thank you for the question. I think it's very common question. So the amount of energy for any protection, of course, as I explained, will be governed by the volume of the rock mass and from what height it is, let's say, getting detached and rolling down. So the range of solution will basically depend on the volume, or let's say the amount of energy. So typically the rockfall barriers can be used up to typically 10,000 kilojoules. Of course, there are developments under progress for even higher capacities. But when you have energy crossing these numbers, you can go for the embankments, typical embankments, reinforced soil embankments of back-to-back structures, or hybrid structures, which can take even higher energies.
Thank you, Dr. Ratnakar. So another question from Dr. Ratnakar. What is the life cycle of the flexible barrier and delivery systems? First. Second, further design is for most probable event or specific lower probability event.
Okay, so I think again this is very interesting question. So typically the life cycle of the barriers is basically governed by the impact. When exactly you will have an impact. Let's say I have installed barrier now, and if it is not impacted for a number of years, it's not an issue, you know. So the barriers are designed for certain energy. Like Luca explained, there is SEL and MEL. SEL stands for service energy levels, and MEL stands for, let's say, the maximum energy levels. So barriers are designed for, let's say, maximum energy levels. So for example, you say a barrier of 3000 kilojoule capacity. So it's a MEL capacity of 3000. So if that barrier is impacted, let's say, by 500 kilojoule, you know, so it can actually receive multiple impacts of such a low energy. But if it is receiving an impact of the capacity MEL1, then of course that's the service life of the barrier is 3000 kilojoule itself, where you will have to go inspect the barrier and do the maintenance part of it. It could be, let's say, replacement of a screen, replacement of the brakes, or depending on the kind of damage the impact has made, that need to be taken care.
Thank you, Doctor. So we have our next question from Johnson Thomas, and question is for Mr. Luca Gobbin. It's on HelloMac. What is the mechanism of input in HelloMac in landslide warning? How does it collect input to give a timely warning?
Okay, thank you for the question. So the system works by deformation. Okay, it means that as I said, so the HelloMac itself, we can install it on let's say on a structure that detects this deformation, or we can also install, as I said, in kilometer or string gauges, I would say in kilometers, to detect the movements, and then from the kilometer, we have the message of that something is moving. Okay, of course we can set some let's say thresholds for detecting for sending the alert, no, because otherwise on a landslide you can receive you could receive a message every, I don't know, 10 seconds. Otherwise I mean, if it's an active landslide. So this is the way the LMAC works.
Thank you, Mr. Govind. So I guess we are just at the end of the session. So we have taken almost all the questions, and we'll try to answer the rest of the remaining questions via email. And now this is the end of this session, and we ensure that we are having 2 more sessions in this webinar series. And we thank you, all of you, for attending our today's session. We hope this session was fruitful for all of you, as it was for us. And I would like to thank our presenters, Dr. Ratnakar Mahajan, Mr. Luka Gobin, and Dr. Ashish Juneja for their presentation today. And also, I would like to mention that I would like to thank IEI and FIB too for organizing this and giving us a platform where we could reach the participants today we have. And now, as you have the feedback form in the chat box, we request everyone to fill that form. This will help us increasing reaching you with more desired topics. Thank you all.
Thank you.
Thank you. Thank you.
Thank you. Thank you.
Thank you, Luca.